Hello everyone, welcome back to this channel. In today's video, we are going to start with successive differentiation. Successive differentiation, as the name suggests, is going to be something in which we are going to differentiate a given function successively. So let's begin with a function y, which is a function of the independent variable x. We know that the derivative of y with respect to x is denoted by y dash, or we can represent it as f dash x, which means dy by dx. Now if y is a function of x, we know that dy by dx is also a function of x. So we can differentiate this function once again with respect to x, and that is going to yield the second order derivative of y. The first order derivative of y dash is nothing but the second order derivative of y. If you keep on doing this exercise successively, you are going to land into the nth order derivative in general of the given function y for any given n. So this is how we are going to continue and find out successive derivatives of certain standard functions. Yn is called the nth order derivative of y with respect to x, and in some books it's also written as the nth differential coefficient. It's also called nth differential coefficient of y. So let's quickly look at the nth order derivatives of some standard functions. Let's begin with the simplest possible first. Suppose y is an exponential function e to the power ax, where a is a constant. So suppose a is a given constant and we are talking about y, which is e to power ax, then we know that the first order derivative is going to be a e to power ax. y2 is going to be a into e to power ax. So if you keep on differentiating this y successively up to the nth stage, then the nth order derivative would be given by a to the power n e to power ax. Similarly, if you have y instead of e to power x, if you have y as a to the power x for any positive a, then the nth order derivative will be log a to power n a to power x, because we know that dy by dx in this case will be log a into a to power x. So if you keep on differentiating successively, then in the nth derivative you have to get log a n times. So that makes it log a to power n into a to power x. So that's the first function whose nth derivative follows a pattern. So we can easily generalize to write our yn as a to power n e to power ax for every n which is greater than or equal to 1 here. So we have found all order derivatives in one stroke. I mean, we can represent them in one line for any choice of n. This is the rule which is going to be followed if y is e to power x. Now let's move on to the second function, which is sine of a linear in x. Let's say sine of ax plus b. So let's look at what is y1. If y is sine ax plus b, then obviously differentiating it once, we'll have y1 as a cos ax plus b. Now the next level, y2 is going to be a into minus sine ax plus b. So you are going to get alternate plus and minus. Now to observe a pattern here, we must see that a cos ax plus b can be represented as a sign again like this. A out, cos of ax plus b can be written as sine of ax plus b plus pi by 2. So these are simple quadrant rules which help you to deduce that the first order derivative of sine ax plus b is nothing but a sine ax plus b plus pi by 2. This has been intentionally done to observe a pattern in all the derivatives that we are going to find out. So let's look at y2 now. Since y1 has come in sine terms again, so we can differentiate this to get our y2. Now y2 will be a square cos ax plus b plus pi by 2, because we are going to differentiate this with respect to x to get the second order derivative of y. Now once again let's write them in the sine format. So it's again rewritten as a square sine of ax plus b plus pi by 2 plus another pi by 2, which I have written as 2 pi by 2 to observe a pattern that every step is getting an additional pi by 2. So the nth step is going to have n pi by 2 in the argument, and this is how we can generalize the nth order derivative of sine ax plus b. It's nothing but a to power n sine ax plus b plus n pi by 2. This is true for every natural number n. Similarly, on the same lines, we can find out the nth order derivative of cosine of ax plus b also, because it's also going to follow a similar pattern, and we can very easily derive that the nth order derivative of cos ax plus b is a to power n cos ax plus b plus n pi by 2. So these are the three easy ones where observing a pattern is very elementary. Now let's move on to the fourth function, which is a linear in x to the power something. So this power is fixed for us. M is a fixed power. So let's see if we are going to differentiate it once. Let us see what do we get. We know the power rule. When we differentiate a power, it is m comes here, ax plus b to power m minus 1, and then because of the chain rule, the derivative of ax plus b will be a. So there is one a attached and m comes over here and the power reduces by 1 in the first level differentiation. Now let's do one more level differentiation to observe the pattern. What will happen in front of a? Now there will be one more a because you are doing one more differentiation, and also together with m you are going to get m minus 1 attached to it, and the power is going to reduce by 1 more. So repeating this pattern, please observe that at the nth stage you are going to get m, m minus 1, m minus 2, so on till m minus n minus 1, because if you have 1 here, this is 2 here, so m minus 2, m minus 1. Since you are getting m minus n here, you will have m minus n minus 1 here, and the power of a will be n, because at the first stage it's a to power 1, at the second stage it's a to power 2, at the third stage it's going to be a to power 3, so at the nth stage it's going to be a to power n. So this is going to be the general formula for calculating the nth order derivative of ax plus b to power m for any fixed m. N is going to take any value from 1, 2, 3, so on. Also note here that suppose m is a positive integer, let's say 10. Then what will happen? You'll have 10 here, 9 here, 8 here, and after a stage which will up to the 10th stage it's fine, but 10th onwards all the successive derivatives will be 0, because for example, suppose you want to find out the derivative of x square. The first derivative will be 2x, the second derivative will be 2. So square up to second order derivative you are getting something non-zero, but the third order derivative is going to be 0, and all successive derivatives after this is going to be they are all going to vanish, right? So for a polynomial which is a polynomial of degree m, you will have all m plus 1th and higher order derivatives as 0, and that's what we have written here. Now in particular, if you take the power to be -1, what happens is, then it is observing, let's calculate 2, 3 derivatives to observe a pattern. If you differentiate once, what do you get? -1 comes here, ax plus b to power -2. It's simple application of the power formula of derivatives that we have. Let's do one more differentiation to observe a pattern. Now what will happen? You will have -2 dropped here, a will become a square, and the power is going to reduce further by 1, -1. So -2 -1, that makes it -3. So you keep on differentiating like this. At the nth stage you are going to get how many negative signs? N negative signs, because in the first order derivative you are getting a single -1, in the second order derivative you are getting 2 negative numbers. So in the nth stage you are going to get -1 coming n times, and rest of it is going to be 1, 2, so on up to n, which is n factorial a to power n ax plus b to power -n minus 1. This is true for every n. For every natural number n, the nth order derivative of ax plus b inverse is going to be given by this. Now this has a very straightforward corollary. Suppose you have y as log of ax plus b, then its first order derivative is nothing but a upon ax plus b, because it's going to be 1 upon ax plus b into a. So the first order derivative of log ax plus b is a upon ax plus b. So the nth order derivative of log ax plus b will be the n minus 1th derivative of the first derivative. That's how we define the nth derivative. It's the n minus 1th order derivative of the first derivative. But the first derivative is a upon ax plus b. And we know the derivative rule, the constant goes out, and we do have a formula. We just did the formula for ax plus b inverse above. So we can just replace n by n minus 1 here to get this formula for log ax plus b. It's very easy to verify. If you do it on your own, you'll understand it's nothing. It's cakewalk, because y1 is already 1 upon ax plus b. A goes out. It's a constant. So you just have to differentiate 1 upon ax plus b n minus 1 times more. So you can use the above formula, replacing n by n minus 1. You're going to get the deduction for the nth order derivative of log ax plus b. The next derivative that is a standard one, which is to be covered. Then before we practice problems, let's cover one more standard formula. It's a product of exponential into sine, or exponential into cosine is also done in a similar fashion. So suppose there is a composition, there's a product of exponential into sine of bx plus c. So you have e to power ax, which is type 1 question. Then it is multiplied with sine bx plus c, which is a type 2 question. So you have a product function appearing here. Let's see if any kind of pattern is followed in this particular function or not. So let's differentiate once. When we differentiate once, since it's a product of two functions of x, so product rule will be applied. First function as it is into the derivative of sine bx plus c, which is b cos bx plus c. First function into the derivative of second, plus second as it is into the derivative of first. So this is the formula that you're getting for y1. Now imagine if you try to handle this and move to the second step, then you will have two terms coming out of this, because it's again a product of two functions, product of two functions. So to simplify our job, we use a notation here. We introduce polar coordinates here. We introduce r and phi in such a manner that whatever is coming in the exponential power, a, the constant, let's call it as r cos phi. And whatever is coming inside sine, the b, the constant b, let's call it as r sin phi. If a is r cos phi and b is r sin phi, you substitute here. What do you get? y1 is r, b, I'm just substituting r. R goes out, b is r sin phi. So you are replacing this by r sin phi and this by r cos phi. So r e to power ax is going to appear in both the terms, and inside you will get a formula which is a straightforward formula of sine of a plus b. Okay, sine c plus sine d, that formula. So r e to power ax goes out. You have sine phi cos bx plus c plus cos phi sine bx plus c inside the bracket. But this is a standard formula. We know that sine of c plus d is sine a, sine c cos d plus cos c sine d. So that's the formula that we are applying here to write it as sine of bx plus c plus phi. Now this helps us to observe a pattern in the next order derivative, because now it has taken the same form. It's exponential into sine of something with this constant awaiting outside. So when you do one more differentiation, we can easily follow this formula to make a pattern out of it, because in the next level you will get one more r, so it will become r square. Exponential becomes the same exponential, and now sine is going to be incremented by another phi plus phi. That's going to happen in the second level differentiation. So this way we are able to observe a pattern. If we retain the form in the product like this is a product of two functions, this is again a product of two functions. So in y2 you are going to get 2 from here, 2 from here. So it will be difficult to handle 4 terms, and like that in the next level you will get 8 terms. So to avoid that, this notational convenience has been introduced. You call your a as r cos phi and b as r sin phi, and observe that in terms of r and phi it takes the shape of a formula, and that formula is simple trigonometric formula of sine c plus d. So that makes you to visualize this as a pattern being observed in every level derivative that you take. So in the first level you will just have r. In the second level you will differentiate once more to get one more r and one more phi added to the argument. In the third level you will get one more r. So it's going to become, third level is going to become r cube e to power ax sine bx plus c plus one more phi will be added, so it's going to become 3 phi. So at the nth level it's going to take the shape r to the power n e to power ax sine bx plus c plus n phi, where r and phi have been introduced by us, because a was r cos phi and b was r sin phi. So what is r? Squaring and adding, you see that r is under root of a square plus b square, which is given to us. These are known constants. They were appearing in the question itself. A and b were appearing in the question. So r is nothing but the under root of a square plus b square, and phi is nothing but the tan inverse of b by a. By b by a we mean this is r sin phi, this is r cos phi. So you can see that tan phi is b by a. If you divide them, you get b by a is tan phi. That means this phi which is appearing in the argument here is nothing but the tan inverse of the ratio b by a, and b by a were the known constants. So you have not introduced anything new here. It's just the notation r given to the under root of a square plus b square and notation phi given to tan inverse of b by a, so that we are able to observe a pattern here in the nth order derivative. Now similarly, if you have a product of exponential and cosine, you can deal with this question in a similar fashion to get your pattern as r to power n e to power ax cos bx plus c plus n phi. So these were some standard questions which you are expected to know. These are some standard nth order derivatives which one is expected to know to handle other sorts of questions. So if you have a straight exponential with a constant a attached to e to power ax, then this is the pattern which is being followed. If you have sine ax plus b, then it's a to the power n sine ax plus b plus n pi by 2, which happens to be the nth order derivative. Cos follows a similar format. Then handling powers is easy, and if the power is a positive integer, then you should understand that after a finite stage all derivatives are going to be 0. Then in particular we handled the inverse 1 upon ax plus b, and log came out to be a particular case of 1 upon ax plus b formula, because the first order derivative of log is 1 upon ax plus b format with a constant attached to it, and these two are the special ones which made you put in some effort to visualize the pattern, because in the original form the derivatives were increasing at every stage. You had 2 terms in the first order derivative. For the second order derivative you will have 4 terms, because every time you will be applying product rule to every term involved. So every term is going to split into 2 terms when you apply the product rule. So handling those derivatives will be very, very difficult unless you use this substitution and apply your trigonometric formula of sine c plus d. So that makes you observe a pattern in terms of to introduce notations r and phi, which have a usual meaning in polar coordinates. R is under root of a square plus b square, and phi is tan inverse b by a. Similarly, you have a very similar formula appearing for e to power ax cos bx plus c. Now let's use these formulae to find out the derivatives of something which is not straight in terms of these standard derivatives, but yes, you can do something to make them come in this form and then use the formula straight off. For example, look at question number 1. It's x cube upon x square minus 3x plus 2 given to us, and we are expected to find the nth derivative of this function. Now nth derivative, if you try to do it ab initio, it's going to be huge, because you will be applying quotient rule, and quotient rule will be very difficult to manage after 1 or 2 stages, and you will not be able to observe the pattern. So in all such questions where you have rational functions given to you, you first divide these polynomials, use normal division algorithm to write your polynomial upon polynomial in this format, and do partial fractions to split it in this form. Now if you write it in this form, it's very easy to handle it, because x plus 3, the derivative of x plus 3, the derivative of x, the first order derivative of x is 1. So every subsequent derivative is going to be 0. The first order derivative of 3 is 0. So you don't have to really bother about x plus 3 when you're talking about higher order derivatives. You just have to bother about 1 upon x minus 1, which is a particular case of 1 upon ax plus b, and 8 upon x minus 2, again a particular case of ax plus b. So using division algorithm and partial fractions to rewrite your question like this is going to make your life very easy, and you can straight away apply the formula of 1 upon ax plus b derived above as number 5. This formula is going to save you, and you will be able to get the nth order derivative very easily. If you do not do division algorithm and partial fractions, handling this rational function will be very difficult, because rational function, when you differentiate, it's going to be done using the first order derivative is going to be done using quotient rule. So you can imagine the extent to which you are going to get terms, and it's going to lead to 2 terms. And then for the second order derivative, you will once again use quotient rule. So it's going to really become cumbersome to handle. So it's always advisable to convert your rational functions into partial fractions and make them take the form 1 upon ax plus b, and then do the question. So this is the answer. Please apply 1 upon ax plus b on your own and see that this is the answer that is going to appear. It's very easy to verify once you look at it as a particular case of 1 upon ax plus b, because 1 upon x minus 1 can be visualized as 1 upon ax plus b with a equal to 1, b equal to minus 1. Here a is 1, b is minus 2. So that's the formula that we have applied here to get the nth order derivative for every n. This is obviously greater than 1 because I did not take the derivative of x here. The first order derivative of x is 1 and all other higher order derivatives are 0. So I am intentionally writing it like this because we are interested in higher order derivatives. We are generalizing. So obviously 1 or 2 derivatives in the beginning are not going to matter if they are not following any pattern. So let's look at the second question, sine square x. Now mind it, we know the formula for sine 2x. We know the formula for sine ax plus b. So we know the formula for sine of a linear in x or cosine of a linear in x. But we do not have a formula for sine square x. We do not know how to handle powers. But yes, you do have trigonometric identities which come to your rescue when you use them. You are able to convert powers into arguments through usual formulae that you have. You know, cos 2x is 2 cos square x minus 1 or 1 minus 2 sine square x. So using that formula, you can write your sine square x as half minus cos 2x by 2. And luckily, you have brought the power 2 into the argument of the cosine function. And cosine of ax plus b, we know how to manage because we have done it as a standard formula here as number 2. The function number 3, sorry, because number 2 was sine ax plus b. So you can see number 3 is cos ax plus b. So if you apply that formula here in particular, then it's easy to see the first order derivative of half is going to be 0. So you don't have to consider this term, and half from here goes out, minus half goes out, and then it's the formula for cos 2x only, which is a particular case of ax plus b with a as 2 and b as 0. So it's going to be a to power n. So that means 2 to power n cos ax plus b plus n pi by 2, which has been simplified like this. So it's easy to handle sine square x, cos square x. In fact, it's easy to handle sine cube x because we do have a formula for sine cube x also in terms of sine x and sine 3x. So doing that here and using the standard form sine ax plus b, sine ax plus b, both of them take that form for different choices of a and b, and you use the formula straight away to get these results for the nth order derivative. You can even try this question for cos cube x because you do have a formula for cos cube x also in terms of arguments of sine and cosine. So let's move on to the next question. Look at this. This is again a rational function. I told you whenever you have a rational function, p upon q kind of a function, polynomial by polynomial, always factorize, do partial fractions. So if you do partial fractions, you can easily convert them into the form 1 upon ax plus b, for which you know the nth order derivatives. So it's just simple partial fractions calculations which lead this form of y, and once you convert your y in this form, writing yn is just a straight application of the formula that we have derived above. So this is also easy. Now look at the fifth question. Such questions also luckily can be managed because we do have our trigonometric formulae which help us to convert these two, the product of these two, into a simple cosine, difference of two simple cosines for which we know the answer already. So writing sine 3x, sine 2x as half cos of 3x minus 2x, which is cos x, minus cos of 3x plus 2x. So that's the standard formula that I've applied. Now for cos x, we have to visualize cos x as cos ax plus b type with a equal to 1 and b equal to 0, and similarly cos 5x as cos ax plus b with a equal to 5 and b equal to 0, and just applying the formula you get your yn like this. This is also true for every n. Now instead of the product of two sines, you could have product of three sines or three cosines as we have in the next question. You'll have to apply the trigonometric formulae successively to first write your y in this form where you have cos ax plus b independent in all the terms. So you can see that converting y into this form using a standard formula is that additional exercise that you need to do for writing the nth order derivative. Rest is usual because you can straight away apply the formula for cos ax plus b for particular choices of a and b in each of them to write your nth order derivative for every n. Now for practice, I have written some questions here. Please practice this. This is again a simple one. We have already handled a question of this type where we had the product of two sines, two cosines. So let's handle one sine, one cosine also in the similar fashion. You just have to use the appropriate formula to convert into 2 cosines or 2 sines or 1 cosine 1 sine, and then straight away use the formula. Now look at this, exponential into cos square. We know exponential into cos bx we know, but we do not know cos square. So please use the double angle formula to convert it into cos 2x, something involving cos 2x, and then handle this question. Similarly, you have this product of 2 sines, a very similar question we have done above, product of 2 sines. So it's very similar to this exercise. And then you have 1 upon x square minus 1. I told you rational functions are done after doing partial fractions. You can split it easily into x minus 1, x plus 1 in the denominator, and then do partial fractions to make them look like 1 upon ax plus b, two different 1 upon ax plus b, and then use the relevant formula to get your nth order derivative. Now here is a list of some important trigonometric formulae which will be useful for you to handle these questions. So please write them in your notebook or take a screenshot of this set which I have written for you, so that you can handle all the questions easily, because we just have 6-7 standard forms for which we have derived the nth order derivatives. For rest of them you have to convert them into those forms and then apply the formula. Otherwise it will be very difficult for you to handle even the second or third order derivative, what to talk about nth order, because observing patterns is not that easy unless you convert them into those specific types which we have discussed in the beginning of this video. So sine 3x is this, cos 3x, then we have double angle formulae, then we have sin s plus sin b, sin s minus sin. These are routine formulae which you know from your class 11, class 12, whenever trigonometric formulae are introduced. But you need to brush up your formulae so that you do not do any mistake while converting your question into the standard forms. Cos a, cos b, cos a minus cos b. Then, so these are sum to products. And then you have products to sum also. So I've listed all the useful formulae for you here. At one glance you will have them. So you can take the picture of first 8 as the first screenshot. You can take the picture of this, and then rest 8 you can take in the second capture. So these are the 16 main formulae that you will be requiring for converting any kind of question into the standard form and then handling the nth order derivative. So I hope you have understood the idea of nth order derivative. Nth order derivative is nothing but the derivative of the n minus 1th order derivative. So this chain keeps on moving successively, and that's why this topic is called nth order differentiation or successive differentiation, because you are finding higher order derivatives of the same function. And finding higher order derivatives is all about identifying patterns, and identifying patterns is not that easy in all the functions that are given to you. So you try to convert them into one of the standard forms through your knowledge of trigonometry or whatever you know, partial fractions, division algorithm, etc. Put them in the standard form and then try to apply the formula for making your life easy. So I hope you have understood the idea of successive differentiation. In the next video we are going to learn about something called Leibniz theorem, which is a theorem which helps you to find out nth order derivatives of the product of two functions of x. You'll be given product of two functions of x, and this theorem is going to tell you a way of dealing with such products and how to find out the nth order derivatives. So we are going to discuss that in the next video. Till then, please practice problems on finding nth order derivatives through whatever we have discussed in today's video. If you like the video, please share forward. Thank you so much for watching.